For decades, artificial intelligence relied on pure calculation to solve board games. It would look at the board, map out every possible move, examine every countermove, and assign a numerical value to each position to find the path that minimized its chances of losing. That exhaustive approach works until you run into the branching factor. Every time a piece is moved, the number of possible future board states multiplies. It creates a cascading tree of potential futures that expands exponentially with every single turn taken. That mathematical explosion is why the ancient game of Go broke traditional AI. A standard 19 by 19 Go board allows for so many overlapping permutations that the number of possible configurations easily exceeds the number of atoms in the observable universe. A computer trying to brute force every single possible outcome would run out of time before scratching the surface. Worse, a mid-game Go position is highly abstract, meaning the computer lacks a clear numerical value to tell it who is actually winning. If the computer cannot calculate the end of the game, it must change its objective. Instead of seeking a perfect, guaranteed path, it has to find a way to estimate the value of a move using only the fragmentary data it can actually reach. Imagine an AI in the middle of a tournament. The clock is ticking, and it has only a few seconds to construct a digital map of the future and choose its next move. This diagram shows the logic it uses to survive those seconds, an algorithm called Monte Carlo Tree Search. It runs on a continuous 4-step loop. Step 1 is selection. Starting from the current board state at the top, the AI travels down the branches of its established decision tree, looking for the most promising path. Which branch it selects depends on a mathematical tug-of-war. The system is constantly pulled between two competing urges, exploiting the known moves that have a high win rate, and exploring completely untested strategies. It balances these urges using an equation called the upper confidence bound applied to trees. If the AI relies too heavily on nodes packed with successful data, the equation physically forces it to pull away and look at the empty, untested branches. By mathematically enforcing this curiosity, the search avoids the trap of local optima. It refuses to stay in a safe, familiar strategy if there is even a remote statistical chance of finding a better one elsewhere. Once the AI follows a selected path to the edge of its mapped territory, it triggers Step 2, expansion. It creates a new node representing a valid move it hasn't mapped yet. From this new frontier, it executes Step 3, simulation. The AI plays out the rest of the game against itself, all the way to a definitive win or loss. It doesn't use deep strategy here. It just rapid-fires completely random moves until the game is decided. That final result triggers Step 4, backpropagation. The simulated win or loss is tallied, and the algorithm sends that data straight back up the exact path it took, updating the win ratio scoreboard of every single node it touched along the way. The system runs this entire 4-step loop millions of times per second. As the data floods in, the decision tree grows asymmetrically. It thickens heavily around the smartest, most viable strategies, while naturally abandoning the obvious dead ends. By firing millions of random futures into the dark and seeing what comes back, the machine filters out the noise. It organically discovers the optimal paths without wasting computational power on bad ideas. Under this architecture, a machine no longer requires a massive database of human-coded expert knowledge. Give it the basic rules of the environment and the capacity to simulate, and it will teach itself. Because it focuses its computing power purely on the most promising paths, this asymmetrical sampling allows AI to tackle chaotic, non-deterministic spaces. It functions beautifully in environments like Miss Pac-Man, where ghosts react unpredictably in real time. In 2016, this sampling-based logic was put to the test in a 5-game match between AlphaGo and Ray Sedell, a professional 9-dan master. AlphaGo combined Monte Carlo Tree Search with deep neural networks to evaluate the board. During the match, it played sequences that baffled commentators, moves that looked alien to centuries of accepted Go theory, yet consistently outperformed its human opponent. By rapidly simulating millions of possibilities, the machine bypassed human tradition. It became an independent discoverer of its own strategic truths. But relying on selective sampling creates a specific vulnerability.
Because the algorithm actively prunes away branches that look unpromising early on, it can suffer from trap states, a blindness to highly subtle, long-term lines of play that masquerade as bad moves. This algorithmic blind spot is exactly what Lee Sedol exploited to secure his single victory in Game 4. His human intuition allowed him to execute a sequence so deeply hidden from the machine's selective radar that the AI's evaluations completely collapsed. Even with that vulnerability, the algorithm proved a larger point. When faced with a universe of infinite choices, attempting to analyze every single option is a mathematical dead end. True decision-making is achieved through rapid, targeted sampling of the future. It requires striking a perfect balance between trusting the paths you already know and bravely exploring the ones you don't.